The IGMPlot program has been developed for 3 years in our group. It is a recent approach that allows you for identifying and quantifying molecular interactions over a broad range of interactions from non-covalent to covalent bonding. The idea here is to present you the fundamentals of the IGM method and to show you how it can be applied in many situations. By using IGMPlot, you can probe and quantify interactions between two given fragments in a molecular system. You can automatically separate intramolecular from intermolecular interactions. You can address small molecular systems from a wave function, but you can also study larger systems like ligand-protein complexes by only knowing the atomic Cartesian coordinates without any wave function. You can build isosurfaces representing the region of space where the interactions take place. You can estimate also the atomic contributions to a given intermolecular interaction. Then the IGM analysis covers a broad range of interactions, from non-covalent interactions, hydrogen bonding, van der Waals interactions, halogen bonding, and so on, to covalent bonding, agostic interactions, metal coordination, and so on. You can determine the strength of a given bond and its polarization. In this poster, I will show you two movies to present you and to display interaction monitoring along molecular dynamics and along a reaction path. Okay, then let's start the poster description. Among the attractive features of the IGM approach, the IGMPlot program provides you with an automatic workflow, which is very comfortable from a practical perspective. And then the IGM analysis can be achieved with very little preparation, as you will see, using the program IGMPlot, which can be downloaded for free at this address. Okay. Before showing you some applications, a bit of theory, but not too much. The cornerstone of the IGM analysis is the electron density, ρ. And this electron density can be directly obtained by the program IGMPlot using the promolecular approximation, which is the sum of spherically averaged atomic electron density, then not relaxed by means of quantum mechanics treatment. Then it is an approximation and very convenient for very large systems, as we will see later on. Or can be obtained from a wave function supplied by the user and previously obtained by means of quantum mechanics calculations. Given a molecular geometry, this electron density ρ is computed at each node of a grid encompassing the molecular system. In addition to this electron density, the program calculates the electron density gradient at each node of this grid. And this gradient is then broken down into fragment contributions A and B here. Fragments can be either molecular fragments, but also fragments can be atoms. Up to you. Finally, the electron density gradient corresponding to a non-interacting system is built and called IGM, standing for Independent Gradient Model. It is an upper limit of the true electron density gradient, and it represents a non-interacting system. Then, by doing the difference between the IGM gradient and the true gradient, we get a new local descriptor called delta G. And delta G takes non-zero values exclusively for interacting situations. In other words, when the electron density of the two considered fragments clash, then delta G can be viewed as a measure of the electron density sharing between fragments. Next, collecting delta G for every node of the grid and plotting it as a function of the electron density leads to this kind of two-dimensional signature called 2D plot, like this for this water dimer system, where one peak here appears, revealing the hydrogen bonding interaction in this system. One advantage of the IGM approach is to intrinsically carrying information on the strength of interaction. The peak 8 is related to the strength of interaction, as you can see here, for 4 different dimers, here, 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 and here. Also, the volume enclosed by each isosurface in this series is associated with a bond strength calculated at a very high level of theory, as you can see here. Okay, the IGM approach also provides the intramolecular interactions inside each fragment. Coming back to the water dimer here, you can see that in addition to the intermolecular signature, we get an intramolecular signature with a peak here that corresponds to the OH bond in the water molecule. Then, as you can see here, the order of magnitude of the covalent interaction, about 0.5, is much larger than the one observed for the hydrogen bond, 0.06 here. By choosing a given iso value of delta G on the two-dimensional signature, you can build an isosurface now, representing the regions of space where interactions takes place between the two water molecules here. Thus, an advantage of the IGM approach is to extract separately the inter- and intramolecular signatures, compared, for instance, with the conventional NCI analysis based on the RDG descriptor, where all the interactions are represented on the same plot here. Also, on the IGM 2D plot, a non-zero value exclusively corresponds to an interaction situation, while both situations, non-interacting and interacting, are present on the NCI 2D plot here. One important question in using IGMplot is, should I use promolecular electron density or electron density coming from quantum mechanics calculation? I mean derived from a wave function. The promolecular electron density is the sum of simple exponential atomic functions, and these exponential functions are tabulated and stored in the IGMplot program for atoms of periods 1 to 4. It clearly lacks relaxation. I mean relaxation by means of SCF calculations. But this approximate density has shown to provide semi-quantitative similar results to the relaxed one, as long as the computations remain in the non-covalent domain. Thus, promolecular density are useful to study very large systems, typically ligand-receptor interactions, because its calculation is very fast. I mean, few seconds, even for systems very large, having something like 1,000 atoms. And it only requires the geometry as input. And this electron density is calculated by IGMplot itself. As soon as you want to describe strong interactions, I mean covalent bonding, metal coordination, and so on, agnostic interaction, you must employ electron density relaxed by means of quantum mechanics treatment. Therefore, in such cases, the user must supply a wave function input file, and IGMplot will compute the associated electron density. As I said before, the IGM approach is really straightforward. The user has only to supply the definition of two fragments in terms of atom indexes. For instance, here in this titanium complex, the central metal atom has been defined as the first fragment. And the second fragment is defined as the rest of the atoms. As a consequence, the intermolecular IGM analysis reveals all the interactions present between the titanium atom, the first fragment, and the rest of the atoms, the second fragment. Thus, it will include the metal coordination between the titanium atom and the chlorine atom, here and here, or between the titanium atom and carbon atom here. But it also reveals an agostic interaction represented by this isosurface here, involving this carbon-hydrogen bond, covalent bond. On the corresponding two-dimensional signature, we find that the peak for the titanium-carbon coordination bond is slightly higher than the peak for the titanium-chlorine bond, while in comparison the agostic interaction is found to be weaker, which makes sense. The agostic peak is found at around, say, 0.1, which is, however, larger than the hydrogen bonding non-covalent interaction previously shown for the water dimer and occurring at 0.06, if you remember. Thus, once more, you can see that the IgM analysis is able to cover and to rank a large range of different interactions. An advantage of the IGM approach is that delta G takes non-zero values exclusively for interacting situations. Thus, in order to quantitatively assess the strength of an interaction, we can use a simple integration scheme of delta G leading to a score reflecting the interaction strength. Such score can be obtained for the interaction between two molecular fragments, even when these two fragments belong to the same molecule, like here, where it is possible to quantify the intermolecular pi-pi stacking here between the two aromatic rings inside this molecule, here and here. In that case, the electron density has been derived from a wave function obtained at the DFT level of theory. So, you can monitor a specific part of your system during a chemical reaction. In this example, this intramolecular pi-pi stacking interaction has been shown to play an important role in a cyclization reaction and favoring a 5-membered ring cyclization instead of a competitive 6-membered ring cyclization. So we think that IGM can be a useful tool in organic chemistry for mechanistic studies. Okay, so far I have considered the two fragments being two molecular fragments. But when the two fragments are restricted to two atoms, like here, okay, an interaction signature is obtained for each atom pair, and then this leads to a bond-by-bond IgM picture of a molecule like here, where bonds, signatures, are represented by different colors, as you can see on the two-dimensional plot here. You can then build an isosurface dedicated to one given atom pair, here, between this carbon and nitrogen atom, for instance. Okay, at this stage, it could be tempting to associate the bond strength to the peak 8 of the corresponding bond signature, like here for the bond signature in black color for the carbon-nitrogen bond. But our experience has shown that it is really preferable to integrate the bond signature because each bond signature has its own shape. For an atom pair, the integration scheme leads then to the IPSI index. It gives the intrinsic bond strength for the given atom pair. An IPSI scale has then been established here, covering a broad range of interactions. Non-covalent interactions are given in the range 0 to 0.15, transition metal coordination in the range 0.15 to 0.60, and covalent interactions have been found in the range 0.15 to 4, these limits being, of course, only indicative. The IPSI index has nothing to do with bond order. It captures the bond strength and it can be measured without being affected by ring constraints. That is the reason why we call this index the intrinsic bond strength index. And then you can compare IPSI values of different chemical bonds in different chemical environments. The IPSI can even be employed to characterize bond strengths along a reaction coordinate where we know that conventional bond force constants are normally no longer connected to the restoring force concept. For instance, at the transition state where we know that force constant can be found negative. Okay, so being able now to probe a bond in a molecule, you can monitor bond breaking and bond forming during a reaction mechanism. And I'm going to show you now a small movie corresponding to a SN2 mechanism, very well known in organic chemistry. And it has been obtained by performing a so-called IRC calculation, intrinsic reaction coordinate calculation, to get points along the reaction path. Next, an IGM analysis has been performed on each point of this path, reverse and forward the transition state, leading to this movie. Before playing the movie, just have a look at the starting structure. The chlorine atom is in purple here on the left. The oxygen atom on the right is about attacking the carbon atom. Two bonds are monitored within this IGM analysis. The breaking bond between the chlorine and carbon atoms first, and second, the forming bond between the carbon atom and the oxygen atom. Initially, the chlorine-carbon bond signature, in blue here, corresponds to a covalent interaction with a large 0.3 peak 8. It is worth noting that the corresponding isosurface has a spherical shape. On the other hand, the carbon-oxygen interaction is described by a small peak 8 here in the IGM analysis in yellow. The corresponding isosurface has an oblate shape. During the reaction, the two signatures change a lot, of course, as you can see here on the two-dimensional plot. The final peak 8 for the carbon-oxygen bond is 0.6, much larger than the initial chlorine-carbon bond. It was 0.3 if you remember. Also, the shape of this carbon-oxygen bond is now clearly different, displaying an oblate feature here in blue color. Then we see that within the IGM analysis, we get a lot of information on the breaking-forming bond mechanism in terms of electron density sharing, bond features, and bond strength. Okay, in other respects, a recent development allowed us to propose the BAF index, characterizing the bond asymmetry of the electron density sharing between two atoms. This factor is delivered by the IGMPlot program together with the IPSI analysis. This index tells us how much the bond strength between two atoms is asymmetrical and the direction of this asymmetry. For instance, here, for the carbon-fluorine bond, a bond asymmetry factor of 0.335 is found in the direction of from carbon to fluorine. The BAF factor would be exactly 0 in the case of a purely symmetrical bond like carbon-carbon in ethane here. The observed trends across a period of a periodic table or across a column looks like bond charge density polarization, as you can see here, but it is really conceptually different. The BAF factor rather measures the tendency of the local bond strength to be asymmetrical and directed towards one of the two atoms. Interestingly, this BAF factor is very sensitive to the chemical environment of a given bond, and as such, it can serve to quantify short-range inductive attractive electronic effects. For instance, it can detect and quantify the attractive effect of highly electronegative fluorine atoms in the vicinity of a given bond, like here, for instance, where we see that the presence of 1, 2, and finally 3 fluorine atoms gradually polarizes the carbon-carbon bond. Finally, a compelling feature of the IGMPlot program is to carry out an atomic decomposition scheme in order to estimate the influence of a given atom in the intermolecular interaction between two user-selected fragments. Atoms are then colored according to their contribution to the intermolecular interaction. And a VMD, visualization state, session input file is automatically prepared by the IGMPlot program to run the VMD program and to get pictures like here between this ligand in ball and stick representation and this protein in surface representation, where the red color indicates hotspots contributing the most to the intermolecular interaction. I'm going now to show you a small movie of a ligand entering in a protein cavity. The atomic decomposition scheme has been performed on a series of snapshots extracted from a molecular dynamics and revealing which atoms of the ligand and of the protein also contribute the most to the biomolecular recognition. In this example, an organic molecule represented here in ball and stick penetrates a neuraminidase protein represented in surface. As you can see, with the IgM analysis, we can monitor hotspots during the molecular dynamics, both on the ligand and also on the protein. And this way, the IGM tool can be useful to detect which residues of the protein are important for biomolecular recognition, and also which parts of the ligand are the most important for the protein binding. And this is made possible thanks to the automatic workflow provided by the IGMPlot program. I come now to the conclusion. IGM revisits the concept of interaction in chemistry through the concept of electron density sharing measured by the new descriptor called delta G. It can be used to identify and quantify interactions over a broad range from non-covalent to covalent. The integration of this descriptor delta G leads to the quantification of the interaction strength. IGM is based on the electron density, which can be calculated either by means of a wave function coming from quantum mechanics treatment or much faster by using the promolecular approximation, allowing to address very large systems like ligand-protein complexes. And the automatic workflow of the IGM approach allows for monitoring interactions along molecular dynamics and, for instance, reaction paths for organic reactions. Some outlooks now to finish. We wish to improve the IGM energy scoring by leveraging machine learning possibilities, also using extremely localized molecular orbitals, which is a new concept called ELMO. We will be able to go beyond the promolecular approximation by exploiting a quantum mechanics electron density, but still keeping a low computational cost, even for polypeptide and proteins. In other respects, applying the IGM delta G methodology to excited electronic states is one of our projects. So IGM is a free software that can be downloaded at this address, and you will find here the documentation of the program as well as examples and screenshots. So thanks for your interest in the IGM approach, and I hope IGMplot will be helpful to you.